In this lesson, we'll look at transformations of graphs. We're going to observe how properties of graphs of basic functions that we know change when we modify those functions. And the first function will be absolute value. I'm sure you can recall the basic shape of absolute value function. It looks like a V shape. Let's graph it. So that's the basic absolute value of x function, like this. And now we would like to graph a function absolute value of x minus 1. Will this graph be similar to the original one? And if it is similar, how similar and how different would it be? Let's try to find a couple points that belongs to this graph just by filling up this table of values. If x is negative 1, then negative 1 minus 1 is negative 2. Absolute value will give us 2. If x is 0, you can see by yourself absolute value of negative 1 is 1. If x is 1, now we have 0 under absolute value, so the result is 0. 2 minus 1 is 1, absolute value of it is still 1. And 3 minus 1 is 2, and absolute value doesn't change it. So those points are negative 1, 2, somewhere here, 0, 1, over there, 1, 0, here, 2, 1, over here, and 3, 2, over there. Well, we can notice that those points arrange in pattern that is very similar to the original absolute value of x, except that it is moved a little bit. The vertex of the V shape, it seems to be moved to the number 1. Let's connect those points to see the shape. And yes, indeed, the V shape is just about the same as the original basic V shape for absolute value of x, but it is moved one step to the right. Every single point was actually moved one step to the right. So we can record the new vertex of this shape. The vertex is 1, 0 over here. If we want to find the range of this shape, we project as usual the graph onto the y-axis and see what this graph is shadowing, what kind of set of numbers it is shadowing on the y-axis. So you can see that the range starts from 0 and goes towards infinity. So 0 with 0, square bracket, until infinity. That's our range. So what's happened to the original graph of absolute value of x when we want to graph absolute value of x minus 1? As you see, the original graph was actually moved one step to the right. Well, this one step to the right must have something to do with this extra negative 1 inside the absolute value sign. So keep this in mind and we'll try to confirm if this rule happens to apply to other functions as well. So how do we describe the transformation that happened here? Well, we can do it by word, just one step to the right. Or we can use a special sign for this transformation. Since this was actually a translation, we can use a capital T that will stand for translation. And we need to give the direction. Where did we translate our shape? Well, we translate this one step to the right. We translate it by this vector. We can actually name the vector. So we are going to use a sharp brackets like this to indicate a vector, and we are going to give the two coordinates of the vector. The first one will tell us how far the vector is going horizontally. Well, it's one step horizontally. And the second coordinate of the vector gives us the information how far the vector changes vertically. But this time it is just 0 steps vertically. So a vector 1, 0 is actually this vector. One step to the right, 0 steps up or down. I like to use this notation because it's more concise and we don't have to write too much. All the information is already here. So this capital T with the vector 1, 0 denotes the translation by the vector 1, 0. That means by this vector. Let's look at the second function, a modification of original absolute value of x. So again, let's observe the original shape of absolute value of x and plot some points that will satisfy this formula. Okay, so let's develop a few points and try to plot them. if x is negative 1, notice that the first part of the function we already calculated in the previous table, so we could take advantage of it. The value would be 2, and then we subtract 2, so we overall have 0. If x is 0, then this absolute value expression is 1 minus 2, overall is negative 1. And obviously you're welcome to calculate this on your own. If x is 1, then the absolute value becomes 0 minus 2, we end up with negative 2. If x is 2, the absolute value becomes 1 minus 2, it's negative 1. And finally, if x is 3, the first part is 2 minus 2, we end up with 0. Now we're ready to plot those points. Negative 1, 0 somewhere here, 0, negative 1 over there, 1, negative 2 over here, 2, negative 1 here, and 3, 0 over there. As we see, this bending point, this vertex, is at 1 and negative 2. So we predict that the shape will be the same as original v, except that it's moved by the vector that describes the movement 1 to the right and 2 steps down. So the vertex is moved by the vector 1, negative 2. Okay, let's connect those red points. That's our new graph. The vertex is at the point 1, negative 2. As to the range, again, let's project our graph onto the y-axis, and we can see that the whole interval from negative 2 to the infinity will be shadowed, will be taken by the function. So the range is from negative 2 until infinity, and the transformation that we needed to apply to the basic shape of absolute value was a translation by the vector 1, negative 2. So we can record big T for translation and coordinates of the vector. So 1 to the right, 2 steps down. So again, the first coordinate tells us the horizontal translation, and the second coordinate tells us the vertical translation. Okay, let's look again at our graphs and try to observe how the information that is hidden in a formula affects the graph. Like here, we had 1 subtracted from inside the function from the input x, and the graph was obtained by moving the basic graph of absolute value 1 step to the right. While in the second case, we had 1 subtracted from the input x and 2 subtracted from the entire function. So subtracting the 1 from the input x caused that the graph moved 1 step to the right, which means opposite direction than the sign would indicate, and subtracting the 2 from entire function caused that the graph was moved 2 steps down, which means the same direction as the sign indicates. Let's look at other functions. This time we'll look at the reciprocal function. So again, let's recall the basic shape of reciprocal function. This shape has very special feature. It has 2 asymptotes, the vertical asymptote and the horizontal asymptote. Both of them are x and y axis. Let's recall that an asymptote is a line that a graph is trying to approach in the long run. So it could be a vertical line, could be a horizontal line, and later on you will find that there are some other asymptotes, could be slant asymptotes, but for now just horizontal and vertical. Asymptotes do not belong to the graph, but they kind of direct where the graph is heading. So when we look at our new modified formula 1 over x plus 1, which means the original 1 over x we changed by adding 1 to the x, the graph of this modified function will have exactly the same shape as the basic reciprocal function, but it will be moved. And when a graph is moved, the asymptotes will be moved as well. So let's observe what will happen to the graph and how the asymptotes will behave. Let's check a couple points. Let's fill up this table of values. Again, I encourage you to stop the video and do it on your own, and then check if your answers are correct. So if x is negative 2 plus 1 is negative 1, so 1 over it is negative 1. If x is -3/2 plus 1 is like -1/2, but we're taking reciprocal of it, so it's -2. If x is -1, oh, now it's a problem because we'll have 0 in denominator, so 1 over 0 doesn't exist. And that's quite important information because we may predict at that moment already that the vertical asymptote will be moved to the x equals -1 line. That's what's most likely will happen, but we'll check on that. Carry on. Let's evaluate f at -1/2. So -1/2 plus 1 is 1/2, and reciprocal of it is 2. At 0 we have 1. At 1 we have 1/2. At 2 we have 1/3. Let's see, after plotting a few points, if we get a general idea how the shape may look like. So -2, -1, it's here. -3/2, -2. -3/2 is here, -2 is over there. Okay, we may want to check a couple more points, but since we suspect that the graph should have the same shape as the basic reciprocal shape, and the vertical asymptote will most likely come through the -1, there is a big chance that the graph will bend somehow like this. And if we are still not sure, we should check more points. For example, if I choose a point -3 for x, then the value of my f function will be -1/2. So -4, -1/2, oh yes, it confirms the graph will go somehow like this. Okay, but let's check more points on the right hand side of -1. So -1/2, 2, that happens to be here, 0, 1 over there, 1, 1/2 somewhere here, 2, 1/3, it's closer and closer to x-axis. So it looks like the shape start forming. It will go somehow like this. Okay, let's join all those points. Yes, the shape has a vertical asymptote at -1, but it also has the same horizontal asymptote, which is our x-axis. And like I say, if you are still not quite sure, you may want to check a few more points to the right or a few more points to the left. You will see that the value will be closer and closer to 0, but keeping the same sign. So for this branch it will be positive, for that branch it will be negative here. Okay, let's talk about domain of this function. If you project the graph onto the x-axis, every single point will be shadowed except for -1. That's a point that doesn't produce any value because you will have to divide by 0 and that's not allowed. So that's the only point that has to be excluded from the domain. Therefore, we can write the domain of this function is all real numbers, but not -1. The range, if we project our graph onto the y-axis, everything will be covered except for this point 0. There's no value 0. And think about it. If you have a fraction 1 over something, no matter how small this will be, it will never be 0 because it's 1 over something. It's not 0 over something. So a fraction could be 0 only when the numerator is 0, but this will never be 0. So the range is also all real numbers, but not 0. As a matter of asymptotes, the vertical asymptote is given by the equation x equals -1, and the horizontal asymptote is still the same as for the original shape. It is the x-axis, which has equation y equals 0. So we have two equations that describes our asymptotes, vertical and horizontal. Okay, now how can we describe the transformation that we applied to the original basic graph of 1 over x in order to obtain a graph of 1 over x plus 1? Well, the vertical asymptote was moved one step to the left. The horizontal wasn't moved at all, which means that the only movement that happened was a horizontal movement one step to the left. So we can say the original graph was translated by the vector -1, meaning 1 to the left, 0 vertically, meaning no vertical movement. Or just put this in words, one step left. So now let's look again at our final shape. It has two branches and it has two asymptotes. The horizontal one is x-axis, the vertical one comes through -1. Okay, let's look at the second example. This time we added 1 to the x and we subtracted 2 from entire function. So the first part is the same as our previous example, which caused moving the basic shape of 1 over x one step to the left. And -2, you may probably guess what this -2 will do to the shape. Well, it will probably move 2 steps down. But let's see. Let's check our points. Again, we can use the previous table of values as a support. We don't have to calculate again this value because it was already done here. We just need to subtract 2 from the previous column. So at -2, we have -1 minus 2 is -3. At -3 halves, we have -2, -2 is -4. At -1, at -1, the value didn't exist, so we can't subtract 2 from the something that wasn't available in the first place. Therefore, for this function, the value at -1 also will not exist. Doesn't exist. At -1 half, the value was 2, and -2, that gives me 0. At 0, the value was 1 minus 2, so it's -1. At 1, the value was 1 half minus 2 is -3 halves. And at 2, we had 1/3 minus 2, that will be -1 and 2/3. At -3, the value was -1 half and minus 2, so it's -2 and a half. And let's see those points on the grid. -2, -3. That's -2 to -1, so -3 is here. -3 halves, -4, so -3 halves, -4 somewhere there. -1 doesn't exist, so we'll have a vertical asymptote here at -1. -1 half, 0, so it's here. 0, -1 over there. 1, -3 halves somewhere here. 2, -1 and 2/3 somewhere there. It looks like those points will be closer and closer to -2. So most likely we'll have a horizontal asymptote here. And one more point at -3, we have -2 and 1 half. Again, those points most likely will shape around these two asymptotes. So when you graph rational function like this, that's a modification of reciprocal function, the best idea is to graph the asymptotes first. The vertical one is really easy to find. That's the one that comes through the point that is excluded from the domain. So by the way, what's the domain of this function? I'm sure you know it already. This is the same as domain of the previous function. That means all real numbers but not -1. So domain all real numbers except for -1. As a matter of range, let's see first the basic shape and move it so the intersection of these two basic asymptotes will be moved one step to the left and 2 steps down, creating two new asymptotes. One is coming through the point -1 and the other is coming through the point -2. So let's connect the dots. Here is our shape. That's the final shape. Okay, if we project the graph onto the y-axis, everything will be covered until -2. We have to skip -2 and then all other values will be taken as well. Obviously, this graph is proceeding farther like this. So all values are taken except for -2. Therefore, we can write the range, all real numbers, but not -2. And again, we could find this number just by looking at the formula, because 1 over x plus 1 will never be 0. So -2, this whole expression will never be -2. That's why -2 is excluded from the range. And let's write the equation of our asymptotes, the vertical asymptote. has equation x equals -1, and the horizontal asymptote has equation y equals -2. The transformation that we applied to the basic shape was a translation by the vector, and let's look again at the coordinates of this vector. We move the shape one step to the left and 2 steps down. So -1 meaning 1 to the left and -2 meaning 2 steps down. So let's clean up this graph and see the final graph of the modified function. Again, it has two branches, the same shape as 1 over x, but the asymptotes were moved. They were moved in such a way that the intersection between these two asymptotes was moved from the origin to the point -1, -2. As before, -1 you can read by just looking at what's happened to the x and take the opposite sign to the number that you see in the formula. So it was +1, we moved the graph to the left. And movement down 2 is recorded in this -2 from the entire function. So whatever you see by the x, you take opposite sign, and outside of the whole function, you take the same sign. So the vertical movement is according to the sign that you see, but the horizontal movement is in opposite direction that the sign indicates. And the next function is a square root function. Let's see various versions of square root function. When you deal with any even degree root function, first of all, before you start creating your table of values, it would be good to find out the domain. The domain is the set of numbers such that you can plug in for the x and be able to evaluate this expression. But when you evaluate root, you must have the radicand, the stuff that is under the root, bigger equals 0. So that's your first condition. Your x plus 3 must be bigger equals 0. So your x must be bigger equal -3. That's how you find the domain of any root function. Okay, since we already have the domain, we can fill up this spot. The domain is bigger equal -3, so it's from -3 till infinity. And that helps us to know how to build the table of values. We have to take the first point in the domain, because this point will serve like a vertex. You will know where to start your graph. So at -3, the root of x plus 3 is 0, because root 0 is 0. At -2 plus 3, so we have 1, so root of 1 is 1. At 1, 1 plus 3 is 4, so root of 4 is 2. And at 6 plus 3 is 9, so root of this is 3. Now let's plot those points, and now we know that the first point, this first number from the domain, gives us the vertex. Keep in mind the basic shape of the root function, which looks like this. Obviously, this will be modified. You probably can already guess which way this basic shape of a root function will be moved to create the new shape of root of x plus 3. According to our previous observations, because we're adding something to the input x, we should go 3 steps to the left, the other direction. Okay, so my vertex is supposed to be here according to my knowledge about transformations. And my points confirm it. The vertex is at -3, 0. -3, 0 is here. Next point, -2, 1. And next 1, 2. And finally 6, 3. So somewhere here. Let's connect those points. Here's the shape. Obviously we can extend it farther. It will go somehow like this. So let's see the range. The range, that means what kind of values we can obtain. Well, we can start from 0 and go until sooner or later any value can be taken, because this function is rising slowly but still rising forever. Therefore our range starts from 0 and goes towards infinity. The vertex is the first starting point, so it's -3, 0. And the transformation that we applied is translation by the vector -3, 0. 3 to the left and no vertical movement. So overall the final graph is just this green shape. Let's look at the next example. Again, it is nearly the same as previous one, but we're adding 1. How this will affect the graph? To start building your table of values, it's a good idea to look at the domain, but the domain will be the same as in previous case, because our radicand is the same. X plus 3 must be bigger equal 3, therefore x by itself must be bigger equal -3. So the domain is from -3 to the infinity. Let's fill up this box. If x is -3, the root becomes 0, but then we're adding 1, so it's 1. If x is -2, the root is 1 plus 1, so it's 2. If x is 1, the root is 2 plus 1, so it's 3. And finally, if x is 6, the root becomes 3 plus 1, it's 4. Again, let's compare to the basic shape of square root of x, how this shape will be modified to graph the new function, root x plus 3 plus 1. So -3, 1, it's here, -2, 2, 1, 3, and 6, 4. 2, 4, 6, 4, somewhere here. And we can graph this shape starting from the vertex, which is -3, 1. So vertex -3, 1. Graph it. Maybe extend this line. It will go somehow like this. If we think about the range, let's project the graph onto the y-axis. Everything will be covered starting from the number 1, starting from 1. So 1 to infinity, that's our range, this section. And what's happened to the basic graph? Well, it was translated 3 steps to the left, like in the previous case, but also 1 step up. So the transformation that we used, it was translation by the vector -3, 1. And relate this again to the formula. The horizontal translation goes in the opposite direction that the sign indicates, and the vertical translation goes in the same direction as the sign indicates. Notice that any root function, it's really half of the regular sideways parabola that normally would go somehow like this. But since we're talking about function, we're taking only one branch of it. So this is the final graph. Let's put together our observations. To graph a function f of x minus a and plus b outside of the function, we need to translate the graph of the original f of x function by the vector with coordinates a, b, a horizontally and b vertically. Okay, so now let's practice graphing functions without actually using table of values. And the first one, we remember the shape, it's a V shape, so that's the original shape that we should have in mind, but we need to translate this function. How to translate it? So let's recall the translation should be by the vector that has x coordinate opposite to what we see by the x, so it's -2, and the y coordinate with the same sign as we see in the formula, so +1. If we just draw this vector starting from the important point of the basic shape, that means vertex, -2, 1 is such a vector. -2 horizontally, 1 step vertically. So this vertex goes here, and those important points will be moved the same way. -2, 1 up, -2, 1 up, -2, 1 up. Similarly, these points. So we don't have to calculate anymore. -2, 1 up, -2, 1 up. We have quite a few points already. We can connect them. And we have the shape of the function f. No calculation anymore. So that's really a big advantage using transformations and knowing shapes of basic functions. So now we can forget about the basic function and we have a beautiful graph. Let's try the next function. Oh, this time we refer to greatest integer function. So let's recall the basic shape. It looked like this. Remember, that's a step function. This is just greatest integer of x. It has the left-hand point included and the right-hand point excluded on every step. So it looks really like this. Now what we need to do, we need to translate this basic shape of greatest integer function by the vector 0 horizontally and 1 down vertically. So each point will be moved 1 down. So this point, for example, will be here, an entire segment. That point over here, and so on and so forth. So all those steps will be one lower step. So let's try to finish the graph. That's how it looks like. Every single right-hand point is with the open circle, meaning no endpoint. Okay, so now we can get rid of the supporting basic shape, and we have the final graph of our function. And the last example is of a cubic function. Again, recall the basic shape of a cubic function. It's like a snake. It comes through the 0, 0, is symmetrical about the origin, and the transformation that we need to apply to this basic shape is a translation by the vector opposite to whatever you see inside, so it means 1, and the same sign outside, so it means 2, by the vector 1, 2. So this main point, 0, 0, will be moved 1, 2, so it will go somewhere here. The regular point 1, 1 will be moved 1 across, 2 up. The point -1, -1 will be moved again 1 across, 2 up. So the shape looks somehow like this. We can check a couple more points. The regular point 2, 8, somewhere here, will be moved 1 across, 2 up, so somewhere there. Okay, so the snake will be moved a little bit up. Let's connect those dots. It looks somehow like this. So this is our function h of x. Again, we can get rid of the graph of the basic function, and here's our final shape, final graph of the function h. Let's put the scale on the other graph. That was 1, that was -2, and the greatest integer function was called g, and the units are the same. This is 1 and that's 1. So I hope you enjoy graphing by translation because it involves a lot less work. You don't need to calculate a lot of values. You just need to remember the basic shape and recognize the translation that needs to be applied.